Hello everyone. Today I am going to discuss about a topic which is called as FlowNet, and which is a part of the broad area of seepage through soils. Okay, so we will be discussing this FlowNet part, which is a broad area, which is a part of the broad area of seepage through soils. And seepage means movement of water through the soil. Okay, so for that, let us start by drawing a diagram. So, so this is the level of soil. Okay, this is the level of soil. Then in between, let us construct a sheet pile. Sheet pile means it is like a foundation which is in the form of a sheet. Okay, so this will be a sheet pile. To see how sheet piles look like, you can search on Google. You will get the different images. So in between, here you can say this is the top layer of soil. Okay, this is the top layer of soil, and this is the sheet pile. Okay, which is like a sheet and which will act as a boundary. Okay, between these two parts, one on the left and one on the right. This sheet pile acts as a boundary. Okay, so now let me uh, start the situation. Okay, so one second. Yeah, so on this side, on the left side, let us consider that there is water level. There is water level here. Okay, there is the water level here, and on this side, on the right side, let us consider that the water level is here, and this is 0.25 meter water level, and this one is 2.25 meter water level. Okay, now this 2.25 meter is the head. Okay, head of water on the left, and 0.25 meter is the head of water on the right. And obviously between this left part and the right part there is a head difference, and whenever there is a head difference there is a flow of water, and the flow of water will be from higher head to lower head. Okay, as if you remember, like if in the Darcy's equation, the cross-sectional area, suppose this is L, okay, and the cross-sectional area, suppose A. So the discharge was what? KIA, isn't it? And what was I? I is equal to delta H by L. So delta H is nothing but suppose H1 minus H2 by L, isn't it? So suppose this one is H1 here, the head here is H1 and the head here is H2. Okay, so there the H1 and H2, there will be a head difference, so there will be a flow of water. Okay, and generally the flow of water happens from higher head to lower head, so H1 will be greater than H2. Okay, so that is the thing that you need to understand. There should be a difference of head, and then the flow of water will occur, and the water will flow from higher head to a lower head. Okay, so now let us go back to the situation that we are discussing. So from the left side the water will start flowing to the right. Okay, so suppose this is a point from which water will start flowing. So water cannot directly flow from here to here. Okay, water cannot directly flow like this because there is a boundary which is the sheet pile. Okay, because there is a boundary which is the sheet pile, water cannot flow. So water will have to take a longer route. Okay, so let me show you how the water will be flowing. The water will start flowing by taking a longer route like this. Okay, because it cannot pass through the sheet pile. Sheet pile is impermeable. Okay, so it has to take this path. So another particle of water, suppose from here, okay, if it has to flow, then it will take a route like this. Okay, and another particle, if you consider from here, particle of water, if it has to flow from a higher head to a lower head, it will take a route like this. I hope you have understood what I have said. Now let us consider that this is a impermeable layer here. Here the layer is impermeable. It means water cannot pass through this layer. Okay. Now at this point, suppose at this point, the head is 2.25, isn't it? 2.25 meter. Here also the head is 2.25 meter. Here also the head is 2.25 meter. And here the head is 0.25. Here the head is 0.25. Here the head is 0.25. Okay. Now one point will be like this. One particle of water which is in touch with the sheet pile, like this. The particle of water which is in touch with the sheet pile, what it will do is, here also the head is 2.25. If we consider this particle of water on the left which is in touch with the sheet pile, it will flow through the boundary of the sheet pile like this, flow through the boundary in touch with the sheet pile like this, and it will move like this. Okay, and it will reach here, and here the head is 0.25. Okay, now so I hope you have understood. The particle of water here will be in touch with the sheet pile that I just considered. Okay, so likewise there will be particle of water which will be flowing from here to here, from here. Actually, it will flow from all the points, like here, from everywhere it will flow. But I have considered just three paths. Okay, I have considered three, but there will be numerous particles, isn't it, which will be flowing. But I have considered just a few. Now, here the head is suppose 2.25. Now here the this particle which is starting with 2.25, when it will reach this point, the head here will be 0.25. So as it moves along like this, its head will start decreasing, isn't it? Its head will start decreasing as it's moving along. So here maybe the head is suppose 2. Here maybe the head is suppose 1.75. Okay, so constantly it will start decreasing, and ultimately at this point, at the end, it will reach 0.25. Similarly, this particle, it will have an initial head of 2.25. Then at some point maybe here the head is 2. At some point maybe here the head is 1.75. And ultimately the head will start decreasing, and here when it will reach, it will become 0.25. Okay, so the head will decrease along the way when the particle is moving from the left, this is from the starting point, to the right, which is the ending point. Now let me just erase the numbers so that it will be easy for me to draw. So now okay, let me just give you some additional detail here. Also, suppose this particle, here it is 2, suppose here it is 1.75, like this it will go. Suppose here it is 2, here it is like this it will go. Okay, now when you join these points, okay, when you will be joining these points, these will be points of what? Equal head. Or when you will be joining these points, at each point the head will be equal. Are you getting my point? At each point the head will be equal. Suppose one particle is flowing from here. Here the particle is 2.25. So when it will reach here, here also the head of that particle will be 2. Okay, so these lines will have this particular one line will have a same head. Okay, now here this line will have the same head, 1.75. Okay, so these lines are generally called as equipotential lines, lines of equal head. So this line will have the same head of 2 meter, and this line will have the same head of 1.75 meter. Okay, so these lines of equal head are called as equipotential lines. So I hope you have understood. So now let me erase this erase a few numbers so that it will be easy for me to complete the diagram. So till now I hope you have got the idea. So just wait till I complete erasing these. Just bear with me. Okay, so now these lines, what they signify? These lines signify the flow of water. So these lines are generally called as flow lines. Okay, these lines signify the flow of water. So these lines are called as flow lines. And these lines, if I try to draw it here now, let me just draw the equipotential lines. It will look like this. These will be called as the equipotential lines. Okay, so there will be numerous equipotential lines, but I'll be drawing just a few. So I'll extend this drawing and I will complete this ones, and you copy this drawing along with me. Let me make it little bit more proper. So these equipotential lines, it will reach the impermeable layer here. Okay, I'm just extending it. So in these equipotential line, maybe it will reach it somewhere far away. Okay, it will reach the impermeable layer somewhere far away. So let us assume that we cannot show it in the diagram. Okay, it will reach the, obviously it will reach the impermeable layer here, but it will be somewhere far. And similarly, since these flow lines, we know the beginning and the end. Okay, so there will be one flow line, maybe like one particle which is somewhere very distant. Okay, on the left side, when it will start, it is somewhere very far away, and it is flowing, and ultimately we can just show a part of it like this. Okay, maybe like a part of it in this manner, and it will reach somewhere very far. Okay, and it has been flowing like this flow line, somewhere it has started very far away, and we can just show a part of it. Okay, so let me just complete it properly now. So this is how we draw the flow net. Okay, it is a net comprising of flow lines, which are these. Okay, and equipotential lines, which are what? Which are these and these. Okay, so flow lines and equipotential lines, they form the flow net. Okay, so now I hope till now you have understood. So between any two flow lines, okay, between any two flow lines, the area that is there, it is called as the flow path. Okay, so if this one is if we consider this flow line and this flow line, so this area is called as the flow path. Okay, so between any two flow lines, whatever path is there, that is generally called as the flow path. So please try to be very get yourself very comfortable with this diagram. Flow path is also called as flow channel. Okay, flow path is also called as a flow channel. So names are different, but the meaning is same. It is the space between any two flow lines. Okay, so now let us go to the main part um, of this whole topic of flownet, we have to develop the equation of flownet. So how will we do it? How will we develop the equation of a flownet? So for that, we have to do a we have to take into consideration a few parts. Okay, so for that, what we will do is we will take a certain part of this flownet into account. Okay, so for example, let us take let us take this part of the flownet for analysis. Let us take this part of the flownet for analysis. So if I draw it in another sheet, how will it look like? I'm just drawing it in a bigger way. Okay, if you can relate it, just see the previous diagram. I'm just drawing a macroscopic version. Okay, I'm just drawing a macroscopic version. Just see this one, see this figure. Okay, and just try to see this one. This is a macroscopic version. So which one are the flow lines? Tell me. So these are the flow lines which shows the movement of water. And which are the equipotential lines? So equipotential lines are these one. Okay, so what will be the flow path? Flow path or flow channel? Flow path or flow channel will be between any two flow lines. I'll just erase it, but I will show. This one is one flow path. This is between any two flow lines. So this one is one flow path, or we can say flow channel between any two flow lines. This is called as the flow path or flow channel. Flow path or flow channel. Okay, so let me erase it and continue with this diagram. Please bear with me while I erase it. Okay, so now uh, this space, okay, suppose if we consider one small space between, which is made by two flow lines and two equipotential lines, isn't it? This is a space made by two flow lines and two equipotential lines. So that is, this space is called as field. Okay, I hope you will understand this. Let me erase it. So this space will be called as a field. Okay, so now suppose in one field, let me consider the dimensions as b1, and this field I consider the dimension as a1, and suppose this one is field 1. Now let us consider this one as field 2. Here let us consider the dimension as a2 and b2, and suppose this one is field 3 and the dimensions are a3 and b3. Okay, so uh, generally these fields are taken as elementary squares. Okay, so it is assumed that these fields are actually squares, elementary squares, elementary. These fields are considered as elementary squares. So what will happen if the fields are considered as elementary squares? Then a1 by b1 is equal to a2 by b2 is equal to a3 by b3 equal to 1, because they are squares, right? So the sides will be equal. So that you have to uh, understand. Okay, the fields are assumed to be squares, elementary squares. So the ratio will be 1. And then let me now take into account the flow. Okay, let me take into account the flow which is happening through field 1. Let me take into account the flow which is happening through field 1, field 2 and field 3. So the flow that is happening through field 1, let me consider it as delta q1. The flow that is happening through field 2, let me consider it as delta q2. And the flow that is happening through field 3, that is delta q3. Okay, now the flow is always constant between any two flow lines. So that you have to understand now. Between any two flow lines, suppose this one is one flow line and this one is another flow line. So between any two flow lines, the flow is always constant. So if the flow is constant between these two flow lines, so we can say that delta q1 equal to delta q2. We can say it, isn't it? We can say it. And let me take into account one more thing. Between these two equipotential lines, suppose these two equipotential lines, the head is suppose delta h1. Okay, now in field 2, suppose the change of head is delta h2 in field 2. Now field 2 and field 3 are between the same equipotential lines. Okay, field 2 and field 3 are between the same equipotential lines, and the change of head between same equipotential lines is same. Okay, so we can say that if delta h3 is the change of head in field 3 and delta h2 is the change of head between field in field 2, and this field 2 and field 3 are between the same equipotential lines, so delta H2 can be said to be equal to delta H3. Once again I am repeating, delta Q1 and delta Q2 are same because the flow through field 1, that is delta Q1, and flow through field 2, that is delta Q2, are between the same flow lines, this flow line and this flow line. Okay, and the head change of head means delta H2 for field 2 and delta H3 for field 3 are same because this flow is between the same equipotential lines. So the change of head between two same equipotential lines, which are these and these, the change of head is the same. So first we can write this one and this one. So delta Q1 is equal to delta Q2 and delta H2 is equal to delta H3. So now let us get back to the most important part of our uh, analysis. For that, let me erase this part. I have to erase and make some space. I want to do the analysis here itself. Okay. Now, uh, if I want to use Darcy's equation, so Q is equal to what we can write? Q is equal to KIA, or we can say K into delta H by L into area, isn't it? So if I use the same formula for delta Q1, delta Q2 and delta Q3, so delta Q1 will be how much? K. If I consider the permeability as K, because let me consider the whole situation in the same soil. In this whole flow net is passing through the same soil, so K will be same. It will be the property of the soil. So for Q1, concentrate on this field. K delta H will be delta H1. L will be what? The length is B1. The flow is passing through a length of B1. Okay, and area, cross-sectional area will be how much? We take a unit width. Okay, we take a unit width. So the cross-sectional area will be A1 into 1. A1 into 1. Okay, so similarly delta Q2 also we can write it. Okay, so let me write it. Delta Q2 is equal to K delta H2 by B2 A2, and delta Q3 is equal to K delta H3 by B3 into A3. Okay, so I hope you are clear about it by now. So now let me write this down in a much proper way. This time I will not draw the diagram. I'll just go on with the numericals. Delta Q1 is equal to K delta H1 by B1 A1. Delta Q2 is equal to K delta H2 by B2 A2. Delta Q3 is equal to K delta H3 by B3 into A3. Okay, so we can just try to analyze one fact. A1 by B1, we know that A1 by B1 is equal to A2 by B2 is equal to A3 by B3 is equal to 1. So we can cancel it out, isn't it? We can cancel it out. So what do we get? Delta q1 is equal to k delta h1, delta q2 is equal to k delta h2, delta q3 is equal to k delta h3. Okay, now we know that uh, delta q1 is equal to delta q2, isn't it? So this implies what? Delta h1 is equal to delta h2, isn't it? Again, we know that delta h2 is equal to delta h3. This implies delta q2 is equal to delta q3, isn't it? Delta q1 is equal to delta q2 because they were in between the same flow lines. So the flow is same between two flow lines, two same flow lines. So delta q1 is equal to delta q2, and delta h2 is equal to delta h3 because this was the head difference between two same equipotential lines. Okay, we have already discussed it. So ultimately we get this, and what is the final outcome of all of it? The final outcome is delta q1 is equal to delta q2 is equal to delta q3. Let me term it as delta q. Then delta h1 is equal to delta h2 is equal to delta h3 is equal to delta h. So delta q is equal to k delta h. Okay, so that is the thing. So now this is the formula with at which we have arrived till now. Now if total loss is h, suppose total loss is h, the total loss is h. So in our case, what is the total loss? 2.25 was the initial, then 0.25 was the final. So total loss is 2 meter, isn't it? So that is what I am talking about. The total loss is capital H. Okay, and let us now go back to one point uh, here. So the total loss is H, okay, capital H, and between uh, any two like equipotential lines, there is a potential drop, isn't it? So suppose here it is 2.25, here it is 2. So there is a drop of how much? 0.25, isn't it? And here it becomes 1.75. Again there is a drop of 0.25, isn't it? So let me do one thing. Let me just erase this part so that it becomes much more clear to all of you. So there is a drop, okay, 1.75. Here it is suppose 1.5. I'm just telling you that constantly there is a drop. Okay, and how many equipotential lines are there now? So suppose here 1.25, 1, then 0.75, then 0.5 point, like this. Okay, so now this is not actually 1.725, then 0.75. So all right, I'm just giving you this example. Okay, it will not be exactly 1.75, it will be something different, but I'm just giving you an example that the drop will be happening like this, 1.25, something like that. Okay, I have not calculated it properly, so just I am giving you an example that there will be drops. Okay, so now how many drops are there? Okay, can you tell me how many drops are there? So there is from here, it depends on the number of equipotential lines that you have drawn. So there is one drop from here to here, there is one drop, two drop, three drop, four drop, five drop, like this. Okay, so in this way there will be drops. Okay, and if I divide this 2 divided by the total number of drops, we get the drop in, we get the head difference in each drop. Are you getting my point? So that is the thing. Suppose here there is one drop, two drop, three drop, four drop, five drop. Okay, then 6, 7, 8, 9, 10, then 11 drops. Okay, so 2 divided by 11 will be what? The drop in 2 divided by 11 will be the drop in each part. Okay, so the drop in each part, sorry, so if you want to know the exactly how much is the potential difference what is happening, how much is the head difference that is going, okay, in each drop, you have to divide the total head, suppose 2, okay, divided by the number of drops. So 1, 2, 3, 4, 5, like this, whatever number of drops are there, if you divide 2 by that, okay, suppose the number of drops is x, then the value that you will get is the amount of head difference in each drop. Okay, and that is nothing but delta H. Okay, so if the number of drops is not generally taken as x, it is taken as nd. Number of drops is taken as nd. Okay, so 2 divided by nd will be, we will get the head difference occurring in each drop. I repeat, if the number of drops, suppose the total head is 2 and the number of drops is 1, 2, 3, 4, like this. Okay, so the number of drops is nd, then you will get whatever value you get, it will be the head difference in each drop. Okay, so that is nothing but delta H, and this 2 is nothing but H, capital H. We take the total head difference as 2. Total head difference is 2, 2.25 minus 0.25, total head difference divided by number of drops. Okay, number of drops will get the head difference in each drop. Okay, so that head difference will be delta H. Okay, so uh, I hope you have understood this part. So in place of delta H also, we can write as what? Delta Q is equal to K into H by ND. Okay, so that is what you need to know. Delta Q is equal to K into H by ND. ND is the number of potential drops. Okay, it depends on the equipotential number of equipotential lines that you are drawing. Okay, depending on the number of equipotential lines in your flow net, you can calculate the number of drops. So we will do a numerical, and in that numerical we will you will be able to understand it in a much clearer way, where we will be taking the values of number of drops, total head and all. Okay, so now you see delta q, we have got k is equal to h, k, no, sorry, delta q is equal to k into h by nd. So that is a flow through one flow channel. Okay, so this delta q is the flow through one flow channel. So we took it as what, delta q1, isn't it? Here it was delta q2. Okay, and everything was equal to actually delta q, isn't it? This is equal to delta q. So delta q was the flow through one flow channel. So you can write this down. Delta q is the flow through one flow channel, and in the flow net there will be more than one flow channel, isn't it? So like this is one flow channel, this is another flow channel, this is another flow channel, this one is this one is another flow channel. Between any two flow paths there is a flow channel. Okay, so in the macroscopic view also you can see here, this is one flow channel, this is another flow channel. Okay, so depends on your flow net, uh, your number of flow channels will be different. So if I consider NF is equal to number of flow channels or flow paths, and delta Q is the flow through one flow channel, so total discharge Q is equal to what? Delta Q into NF. So this implies Q is equal to what? K H NF by ND. So this is the ultimate equation. Q is equal to KHNF by ND. This is where the analysis ends. Okay, don't worry. Once we do one small numerical, then you will have the clearest idea. Okay, for the time being, what you do is you write the notes of this video and submit it before 10:10 a.m. tomorrow on 28th. Okay, so then I will hopefully I will give you I will make a short video on this on a numerical on this topic. Okay, it will be just like for like 5 minutes or 10 minutes. Okay, and then you will have the clearest idea ever. Okay, so thank you very much.